First, thank you very much for this nice workshop. So today it is not a technical presentation, it's more one application of machine learning in a project that we use in K11. So today I will talk about how we can create CME model in for EUHFORIA, so space weather simulations using machine learning algorithm. So, okay, so first I will talk a bit about EUHFORIA. So EUHFORIA is a space weather simulation, and it is divided into two parts. First, we need to run a kernel model, so it can be PFSS or Coconut, what you want. But the most important thing is to have a 3D map of density, radial velocity, magnetic field, and pressure at 0.1 AU. So for maximum activity, for minimum activity, this kind of map. Then, in the second part, we solve the 3D MHD equation in 3D to let evolve the different quantity in the heliosphere. So the aim of this simulation is, of course, to do some prediction. So as you can see here, for one of simulation, and you see the evolution of the density, and you can compare the density predicted by EUHFORIA with the one observed by in-situ measurement. So you can see here, for example, that the density is pretty well reproduced by EUHFORIA. Of course, in EUHFORIA, we need to have some CME model to have some prediction. And for that, we will modify the inner boundary condition at 0.1 AU to model the crossing of a CME. And of course, the quality of the prediction depends on the CME model that we use in EUHFORIA. If you want to have a realistic prediction, you have to use a realistic CME model. And we have different CME model in EUHFORIA. In fact, the most common and the most used is FERMAC. It is a sphere, a linear force-free magnetic field described in the spherical geometry. We also have FY3. So FY3 is a very realistic flap-swap model. It works pretty well. The problem is that it is so much realistic that it needs a lot of time to be computed. So for real-time forecasting, it's a problem. And recently, we also developed new toroidal model. So it's a mix between a spherical model and the flux swap, and we see that it works pretty well. So in details, in one of paper of Richard here, we compare FY3D in green, FERMAC in purple, and the toroidal model in blue. And we see that, so in the toroidal model, it is described by the set of identical equations, magnetic field in this configuration. And we see that the blue curve has the best arrival time. Also, the amplitude of the magnetic field is better than FERMAC, less than FY3D. But on the contrary of FY3D, it has less time to be computed. So it's a bit compromised between FY3D and FERMAC. But clearly, when you see that it is not perfect. It is not perfect because, in fact, in the heliosphere, I am pretty sure that a CME is not described by this set of equations. I mean, it's an analytical solution, but we are not sure that it follows a flat-swap distributions. So, but in EUHFORIA, we need to have solution to be implemented, to be computed to describe the solution. So we need to know an exact analytical solution, and it is a problem. Also, as I said, we need, for real time, we need to have something very fast to be computed, because we cannot ask to one day, or we need to do something quick. And of course, we want to CME models that it fit with optional data as much as possible to fit well this. So the idea of this work, but it is not finished, I will present the idea today, is to develop new CME model that it is not limited by the fact that we know the analytical solutions, and where the magnetic structure fits the optional data. For that, we can use machine learning. So the idea is to take an equation that will describe a magnetic structure, solve it using machine learning. Then, for this particular case, we obtain the 3D surface of the flux swap by solving an equation. So we don't care about the exact solutions. We just want the solutions. Then using the 3D surface, we use the invariance of the toroidal structure to get the structure in 3D. So we have the magnetic field in 3D. And something also new is that we apply a deformation to stretch the torus into a flux swap structure. So using this pipeline, we obtain new CME model in EUHFORIA. For this study, we use the Kirchhoff equation to get the magnetic field. So we use it because we know that machine learning can solve this kind of equation, and we know that this kind of solution, so if you take a particular solution of this equation, we can use it in EUHFORIA. And we solve this equation in neural networks, so a physics-informed neural networks with geometrical parameters that can describe different shape of the torus. So we put in the feature some geometric parameters that will describe the 3D surface, and we put also the location inside the torus. So here it is the ID. There is some work that he already solved this Kirchhoff equation using a pin, using deep learning code, but we improve it by doing different things. First, sure. Can you try now? Yes. Okay, this one. So first, as I said, it will describe it is a parametric pin, so it will describe different shape, and we cannot deal with all the shape possible during the training. So what we want to do is that we select a sample of shape, and we pick some collocation points at each iteration. So we can take 100 in this shape here, 100 in this one, to cover a large range of geometry at each iteration. So at each iteration, we change the collocation points. It is something that it is not always done, but we found that it allows us to deal with more 3D shape. Okay, and also for this machine learning algorithm, we use a physics-informed residual adapted networks. So it is a bit different to a classical neural network works. And we use it because, in fact, we found that we obtain a loss 10 times smaller than using the classical one. And also the error is 4 times lower than the classical ones. So I will describe it a bit. So we have the different feature here. With this feature, we create 2 gates here and here by transform it using 2 dense layers. And then we have a set of a certain number of blocks, where in this block, we insert the result of this layer in between each layer. So it is 3 layers. And at the end of this block, it will combine the result of the 3 layers with the result before this block. And if this block improves the accuracy of the process, we'll take it into account. And if this block is useless, we will put it alpha is equal to 0 to skip the impact of this block. And yeah. And at the end of this chain, we can also put it some physics if you know some points. Okay, so now I can show you the result. So it is a preliminary result. And we apply it for a solution for equation where you know the analytic form to compare the result to compare with literature. And we found that the loss is -7 and it is very good. Trust me, compared to the literature, it's the kind of stock that you want to have. And also, if you compare for different shape, and here it is a difference between the analytical exact solution and the one obtained by your code, and you see that the difference is mainly at the center, but we have less than 1% error between the exact solution and the result provided by the pin. Okay, so what is the next step? Now that we know that the code works pretty well, we want to use it for study a real case in EUHFORIA. And for that, we want to use it for a solution where we don't know the exact solution of these equations. For that, we will use the Grotjov-Renoff equations. So the idea is to, if you have a spacecraft, your spacecraft will have some measurement of the magnetic field, for example, the wind, for the wind, and by doing some very complicated stuff, in fact, we can determine the flux, the 2D flux in the along the trajectory of the spacecraft. And you can obtain this kind of stuff where you see the 2D shape and the flux in the space. And using the flux, you can determine the right term of the Grotjov-Renoff. So with in situ measurement, you determine the right term of the Grotjov-Renoff. Then you solve it using machine learning code, and it provides a CME model for EUHFORIA, a CME model that we are sure that the magnetic field distribution is consistent with the observation further in the heliosphere. So it is a work in progress. We are working on one event, and we are trying to do the Grotjov-Renoff co-construction for one case. Okay, to finish, I would like to conclude. So why this project could be interesting? First, it allows us to have access to magnetic field distributions that we don't know the exact solution because we use a solver. But using a machine learning solver instead of a classical solver is interesting because once the training is done, the inference time is very low, so it does not add some computational resource into EUHFORIA. So it is perfect for real-time forecasting. And I think it is all for the moment, and we'll see what happens if we put some physics in the Grotjov-Renoff equation to have an in situ measurement consistent with the CME models that we use. So thank you very much.
Thank you for a nice talk. Are there questions in the room or online?
In the boundary conditions then for the machine learning? I mean, do you somehow set the values which allow merging, or I mean, I'm not an expert.
Oh yeah, can you go back in one slide before? Oh, okay. In fact, the in situ measurement will determine some magnetic field measurements for the torus. So it should be the initial condition for the model. But it is not mandatory when we solve the deep learning neural network that to say, okay, this point should to have this properties. So we don't need an initial condition for the code. We only need to say, okay, the equation should solve this. The solution should solve this equation, and it's only the only thing that we say that okay, find a solution for this equation.
Yeah, go.
So the input, it's a magnetogram. What's the input of the machine learning model, or the parameters of the?
No, nothing. We only put in say okay, look at this point and this point. Follow. We need to find the flux that is solve this equation for this point.
Okay.
But maybe the question is, how would you use it in
Yeah,
EUHFORIA, this solution?
Operationally, let's say.
Yeah.
Okay, so once you have this solution, so you have the flux, you can derive the flux to get the magnetic field. It's the BR is the flux the derivative of the flux by Z, and B theta is the derivative by R. So you can find the magnetic field using the flux. And then in 2D, and then since it is a torus, you have the magnetic field in 3D, and then since you have the magnetic field in 3D, you let it cross the inner boundary of EUHFORIA, saying that change the inner boundary of EUHFORIA, saying that it is crossing this torus. You model the evolution of the torus.
But maybe the question is, how do you, initialize EUHFORIA? You probably look at, like normally you look at the chronograph image, right? And you estimate the shape of your CME, and here you could maybe
in EUHFORIA, the initial position is this map.
Yes.
And when you initial with CME, imagine a torus crossing this inner boundary. So first you have 1 point. So instead of saying the velocity is 4 and
right.
It is the velocity of the CME, so it can be 7 and
Right. But you need to get the parameters of the CME, right, from the chronograph image.
Yeah.
And those you get from do you fit the shape of your CME to?
That's to it's better. But yes, you can.
So what I understood, that procedure is the same, or we reconstruct to get the geometrical parameters. This is just going to give us the magnetic field parameters, right?
Yeah.
From your solution.
Yeah, for the shape of the torus on the side, we use white light images,
Right.
and you try to.
But the shape would be your boundary conditions that you put, right? As your solutions depend on boundary conditions, or on the shape of the object that you are. So
when you solve it, when you solve this equation, it's a decimal quantity. So then you say, okay, this one is correspond to 2 solar radius with corner white light imaging. But it is you solve it for additional torus, and also, for example, using the 2D shape, it's good to have a parametric code that. No, we can have access. If we say, okay, it's like that, we have a solution for this particular geometry. It's why it could be also interesting.
Okay, so in the end, you're, let's say, improving / accelerating as a part of EUHFORIA, and then you need the magnetogram to have PFSS or WSA or another, or your model.
It's accelerated solutions, I think.
Yeah.
Right, like the solutions of Graf-Shapran. This is a surrogate Graf-Shapran solver.
Okay. I think I got
it like that.
Not for not Soloviev, because Soloviev is when you know the exact solution. No, we don't know. But it's one solver to have access in EUHFORIA, because when the classical way to do it, in fact, is you take the map. You know that Sfermac is crossing. So you determine if it is crossing or not. If it is crossing, you compute the magnetic field at this point. So you need to compute it. It adds some resource into EUHFORIA. And for Sfermac, it's okay, but for 3D, you need to determine all the structure of the magnetic field.
This can take
time. It is why using something that it is already trained.
Yeah.
Okay, you apply it at one point, it gives you the result just like that. So. But it is not published yet, and it will still work.
Okay. Good. Yeah.
Thank you.